Hi, what I have here on the workbench is another interesting combo device sent in from FNIRSI. The model number is DSO-TC4. By casual glance, it looks like yet another component tester because of the socket here, but it actually combines a component tester, a single-channel 10 MHz oscilloscope, and a modest 50 kHz signal generator all in the same compact device. And if you look at the print underneath here, it says Transistor oscilloscope. This is actually quite confusing, as it's definitely not an oscilloscope built with discrete transistors, but rather a component tester and an oscilloscope combo device. On this channel, I had reviewed many combo devices before. The most common ones were the oscilloscope, multimeter, and signal generator combos, which when you think about it, they make the most sense. And then there were those thermal camera and multimeter combos, and they started gaining some momentums recently. Now, this combination seems to be quite interesting. I guess it makes sense from a manufacturer's perspective, as you've already got the hardware for the component tester. Adding in a signal generator and an oscilloscope requires little extra hardware. Of course, when I say little, it's all in relative terms. You still need to add the ADC and other supporting circuitry, but the core logic for the oscilloscope and function generator can be implemented using the same hardware. My guess is that they are using a microcontroller to achieve all these functionalities as opposed to a dedicated FPGA, given the relatively low specs. After combing through the user manual, it seems that it actually does more than just the three main functions that I mentioned. It can even measure voltages, test some temperature sensors, and even claims to be able to decode IR signals. Now I wonder what this little device cannot do. Anyway, we'll test these out a little bit later. Now, I have some issue with the case design. As you can see, it doesn't actually sit quite still. I can spin it around. And the reason is that, if you take a look at the back here, is the hinge here has the FNIRSI printed on top of it. That is actually protruding ever so slightly. And there are no rubber bumpers on the back here, so it's actually pretty difficult if you are using it sitting like this, because it will just spin around and you cannot really pin it down. It does have a stand you can extend. Let me try to pull it out. And also you can see here, we do have some rubber feet here on this side. So presumably, FNIRSI wanted you to send this thing up when using it. So I guess all FNIRSI needs to do is really just to add a few rubber feet here and there, and then you can put it on the back. Also, I wanted to point out, because of the size of the product, FNIRSI actually chose to use these MCX connectors instead of the standard BNC connectors up here for the oscilloscope and signal generator inputs. Now, this is not my favorite design, as it requires you to use either an MCX to BNC adapter, which by the way is included, or you will have to use a non-standard oscilloscope probe, and neither is convenient. Anyway, in the product box, you also get a P6100 oscilloscope probe. It's a 100 MHz probe, more than sufficient for the 10 MHz bandwidth. You also get an MCX to BNC adapter, so you can plug in the standard oscilloscope probe. Also, you get a few clips for the component tester and an MCX to alligator clips cable. And by the way, as a size comparison, here is the FNIRSI LCR-P1 dedicated component tester I reviewed a while back. I will leave a link to that review video if I remember to do so. Alright, time for us to turn it on, but of course, let's actually remove the screen protector first. I just stood it up so that hopefully it doesn't wobble around. Anyway, let's power it on. And now we're greeted with this selector menu. According to the specs, it can measure resistors from 10 milliohms up to 50 megohms, and capacitors from 25 picofarads up to 100 millifarads, and inductors from 10 microhenries up to 1000 microhenries, or 1 millihenry. So the specs here look pretty much identical to the specs on the LCR-P1 component tester. And besides resistors, capacitors, and inductors, obviously you can measure diodes, transistors, MOSFETs, SCRs, so on and so forth. So let's actually take a look. So press OK. And I guess we will put in a few components and try it out. To make my life easier, I plugged in these leads so I don't have to fiddle around with the ZIF socket. Anyway, let's first start with a resistor. And as usual, I'll start with this 100 ohm precision resistor with a 0.1% tolerance. All right, let's put it in. And we'll press the auto button. It does take a while. Yep, it measured 102 ohms. Now, if you want an accurate measurement, you probably need to go to a multimeter. That's not the job of these kind of component testers. The component tester's job is simply to identify the component and give you a rough reading. Of course, the more accurate, the better. but this is not bad at all. So let's test another one. Now let's take a look at a 1.25 kilo ohm resistor. This one has a tolerance of 1%. And close enough. How about a 1 mega ohm resistor? No problem. Obviously, you can see that the value is approximate at best. All right, let's test out a few capacitors. Here is a 68 picofarads capacitor. Let's give it a try. Not bad. The reading is a little bit on the high side, but of course we also have these long leads. Actually, the measurement actually agrees with what is measured by the unit T. The spec says that the minimum capacitance it can measure is 25 picofarads. I wonder if it can measure a 10 picofarads capacitor here. So let's give it a try. And let's give it a go. Now it does take quite a bit of time in capacitance mode here. You can see here is taking 5 or 6 seconds already. And we're measuring 3 picofarads. I guess that's probably not quite accurate. Let's try it again. Okay, so now it's 15 picofarads. I think what happened before was these clips are actually not in contact with the leads. So that 3 picofarads was actually the residual reading. So now you can see that if we subtract 3 picofarads from the 15 picofarads reading, actually the result is not bad. We will measure a few more. And this one, I think, is a 100 nanofarads capacitor. Let's try it out. And 90.1. Actually, that's pretty close, as this one, if I recall, measured right around 85 nanofarads. Okay, so now let's try a 1 microfarads capacitor here. Again, the result is not bad. It even gives the ESR reading. Of course, we don't know whether or not that ESR reading is accurate, but actually let's verify that with the ESR meter. Now, the ESR measurement is going to be a little bit tricky as it's heavily dependent on the measurement frequency. You can see here at 1 kHz, we're measuring about 3.8 ohms in terms of the ESR. Of course, we don't know what the frequency the FNIRSI is measuring under, so we'll have to, I guess, test it out later. But anyway, you can see that the capacitance reading is actually right on. And just to illustrate the point, if I change the frequency, let's see 10 kHz, you can see the ESR dropped significantly. Of course, if we change to 100 Hz, the ESR would increase significantly. So the ESR is definitely heavily dependent on the measurement frequency. So I just took a single shot of the measurement waveform. You can see here, we're measuring right around 2 kHz. Now that is twice the measurement frequency used on the ESR meter. So given the frequency differences here, the ESR measured by the FNIRSI probably is right in the ballpark. And now let's go straight to a 15 millifarad capacitor. It's probably going to take a while as it's a relatively large capacitor here. And no problem, we get 14.5 millifarads. All right, now let's measure a couple of inductors. So the first one here, let's see what this is. And it's shown as a 0.22 millihenry inductor. And let's take a look at the inductor itself. It's 221, so yep, it's 220 microhenry, so that's exactly right. Now let's try another inductor. This one I actually don't know the value, so let's take a look here. So the FNIRSI says it's a 1.23 millihenry inductor with a 2.4 ohm resistance. Let's actually verify that with our LCR meter here. And you can see it is close enough. So not bad at all. Now let's try a diode. This is interesting. This is a single diode. I'm not sure why it's showing up as 2. So let's try it again with these 2 leads. Huh, not sure why. That is really weird. Let's actually try another diode. Now this is a Zener diode, but it should be able to test as a diode as well. So let's give that a try. Yeah, you can see that we are able to test this diode properly, but not the other diode. I'm not sure what is going on here. Let's try another diode. Yep, it's fine. Huh, not entirely sure what's happening with the other diode. Let's try it again, actually. I'm not sure if it's a contact or something else. So this was a diode. We had a problem earlier. I'm genuinely puzzled. And just to prove that the diode is actually fine, let's use the unity meter to verify that. So this is the same diode here. You can see. Let's see here. Yep, no problem. So I don't know what is going on with the FNIRSI with this diode. Now here we have a NPN transistor. The transistor itself is a 3904. And also you can see that the pins were identified correctly as well. The black one is 1 and the red one is 2. The green is 3. So we have the E, B, C here. So at least for this transistor, everything was identified correctly. And here is a PNP transistor, it's 3906. Again, it was identified with no problem. Now here we have a 2N7000, which is a small signal MOSFET. Now I don't know why it's not able to detect that. Let's actually shift the pins a little bit, shift the contacts a little bit, and see if we can do it again. No, not able to. You can see that we were able to detect this MOSFET using the LCR P1. And just to rule out it's not the leads, let's actually use the socket to test this MOSFET here. Nope, you can see that we're still getting the same result. Well, I tried another MOSFET, you can see that we got the same result. So not entirely sure what's going on here. And here I have an SCR, which is a BTW69-600. And you can see that it's not able to detect that either. Now, that said, we were not able to detect this specific SCR using the LCR P1 either. Now, none of the component testers that I had was actually able to detect this specific SCR. This component tester can test Zener diodes as well. If you recall, the LCR P1 also has that capability. Let's give it a try. Now on this meter, the Zener diode measurement is actually under a different menu, so it's not in this component tester menu. Let me show you that. So we need to get to the main menu. And let's go here. We have a menu item called Toolbox, and that's where they place the Zener diode tester under. So let's give that a try. I forgot to mention that for Zener diode testing, you have to use the bottom 3 positions here, marked as KAA. These are dedicated for Zener diode testing. Anyway, let's give it a go. And you can see that we're able to measure the voltage with no problem. I deliberately chose this specific Zener diode because it has a higher voltage, and you can see that we're able to measure that with no problem. The DSO-TC4 can also do continuity test. I guess that's what FNIRSI refers to as the on-off test. Let's give it a try here. Yeah, no problem. And by the way, just like the LCRP1, the DSO-TC4 also supports IR decoding. So let's give that a try. And here I have a remote control. And by the way, this section here, that's where the IR sensor is located. And as you can see that as we press different buttons, we detected different codes. Unfortunately, just like the LCRP1, it can only decode known protocols, and it does not give you the waveform. For example, here I have an IR keyboard. You can see, I'm not sure if you can see the emitted IR signal here, but if you take a look here, it's not able to detect that. So this is where, in my opinion, it would be much more useful if it can show you the raw zeros and ones, and also the waveforms, instead of just the decoded value. Also, you can use this component tester to test out a couple of different humidity and temperature sensors. One is DS18B20, the other one is DHT11. Now, I don't have either, so I won't be able to test it out here. But it just seems to be so arbitrary to add a couple of seemingly random components here and there. Then you can also see that we can do voltage testing with this voltage test menu. Now, the inclusion of this functionality is even more intriguing, as not only it is able to test just up to 40 volts with a resolution of 0.1 volts, they actually designed an input jack just for this purpose only. I mean, I would pretty much assume everyone will have at least one multimeter or two lying around, so I'm not entirely sure why FNIRSI would bother including the voltage measurement with this component tester, especially with a dedicated input connector that can only be used for voltage measurement. Anyway, let's give it a try. Now I'm outputting 1 volt with my MV216A voltage standard, and you can see here we are already quite a bit off. And 2, 3, 4, 5, you get an idea. Now we're going all the way up to 10. So it appears that FNIRSI is just trying to cram as many features as it can into this component tester, whether or not it's useful. So at least it appears impressive on paper. Unfortunately, this practice has somewhat becoming a trend in this kind of low-cost devices, given the cutthroat competition. Anyway, now let's move on to the oscilloscope mode. Together, all you need to do is come back to the menu, and we can cycle through different items here to go to the oscilloscope mode. For the first test, I'm putting in a 1 MHz, 1 volt peak-to-peak sinusoidal. Let's auto-acquire that signal. And no problem, seems like we are able to acquire that signal. You can see that the frequency is 1 MHz and the peak-to-peak voltage is measured at 0.99 volts, so no problem. And you can see that the adjustment is actually quite intuitive as well. I can use the left-right to adjust the time base, and also I can use the up and down to adjust the attenuation. And if I want to change the functions of these arrow buttons, I think I can press OK. Yep, now it changes. For example, now I can change the triggering position, and now I can move the waveforms around. And let me increase the frequency. 2 MHz, 3, 4, 5, 6, 7, 8, 9, 10. And you can see that while the peak-to-peak voltage is still within the 3 dB bandwidth, but the waveform captured has some weird modulation going on. So that definitely means that there's something with the acquisition circuitry. Anyway, so now you can see that when we expand that, actually it's not that bad. It just is wobbling around. Now let's increase the frequency a little bit higher. 11, 12, 13, 14, 15, 16. Yeah, you get the idea. As right now, for example, we're at 16 MHz. You can see that the waveform is dancing around, and also we're dropping below the 3 dB bandwidth. So I would say that the 3 dB bandwidth is probably right around 10 MHz as the spec says. And here we're looking at a 1 MHz square wave, and you can see that the square wave looks relatively clean. Now let me increase the frequency here. 2, 3, 4, 5. Yeah, at 5 MHz you can see that we are not able to adequately represent the square wave. And that is because we have higher harmonics contents that are way beyond the 10 MHz bandwidth. And here is a amplitude modulated signal. You can sort of see the modulation going on here, but it's not able to capture that signal that well. And of course, if I change the time base, you can kind of see that as well, but we're not able to get a stable signal. The carrier frequency here is 1 MHz, and the modulation is at 1 kHz at 100%. And I just lowered the carrier frequency to 100 kilohertz, and you can see that the capture waveform is actually slightly better. And by the way, earlier I mentioned that you can use the OK button to change the different modes, and I think I made a mistake here. So when you change to this, actually it's changing the triggering position. But of course, in this case, the triggering position doesn't really help to stabilize the waveform. Now we're looking at a frequency modulated signal. The carrier frequency remains at 100 kilohertz. The modulation frequency is at 100 Hz with a frequency deviation of 10 kHz. Now, because the update rate is relatively slow, it actually does not represent the actual frequency modulated signal that well. That said, you can kind of see that it's being frequency modulated as the waveforms expands and contracts. But if I change the time base, you will see that you really can't tell this is a frequency modulated signal. And finally, let's take a brief look at the signal generator. Now, the signal generator is actually quite rudimentary. You can see that we don't really have a lot of options here, but we do have quite a few waveforms. You can see here, let me cycle them through. You have a square wave, you have your sawtooth, and so on and so forth. You can see that we have quite a few different ones. And as I mentioned earlier, you can see here, the highest frequency it can go is 50 kilohertz. And if you look closely, you can see the quantization steps here. This is a sinusoidal. You can see the different steps here. Now, just by the look of it, the output deck is probably at most 6 or 7 bits. For square waves, we can also change the duty cycle. Let's give it a try. Let's see here. Let's do 60, 70. Yep, you can see that this works pretty well. One of the major limitations of this signal generator is you can see that the output is actually DC biased, and also the maximum amplitude is capped at 3 volts. While in operation, we're drawing about 350 milliamps, and given a 1500 milliamps battery, the estimated runtime is about 4 hours, which is consistent with what the manual said. Well, again, I'm quite disappointed. I don't know what's going on here, but a lot of the FNIRSI products recently I have done teardown with, all the major chips have their markings removed. And you can see here, we don't have anything on this microcontroller, and we don't have anything on this chip either. At least they left the ADC chip along. The ADC used here is a 3PA1030, which is a 10-bit, 50 megasamples per second ADC. And that is consistent with the 48 megasamples per second oscilloscope sampling rate. Since we only have one oscilloscope channel, we only have one ADC here. So what's my verdict? Well, it's a component tester, and it sort of does its job. Although we were having some trouble measuring MOSFETs, I suppose FNIRSI can probably fix that in a firmware upgrade. In a pinch, you can use it as a very basic oscilloscope and rudimentary signal generator, but don't expect it to be a replacement for your dedicated digital oscilloscope and function generator. Anyway, I hope you enjoyed this review and teardown. If you liked the video, please remember to give it a big thumbs up, and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.